Yes.
Okay. Now in morning session, I have discussed the equal to m by I into y. Sorry, m by y into I. M by I into I. Okay. And where m is the bending moment, PL by 4. And I is a moment of inertia. Okay. That depends upon the cross section. If we select the cross section like this, okay, then you will get the more stress at this location. And same cross section if we take like this, okay, here you will get the more stress at this location, and depending upon the this dimension, vertical dimension, you will get the stress. Okay, so you have to define the CDEF points. Okay, again one more thing, here bending stress is maximum at this location, maximum tension or compression depending upon the type of element. Bending stress is maximum at this location, that also depending upon the tension and compression, okay, or type of element. And at this location you have zero bending stress. Okay, do you agree with this? So bending stress varies across the vertical dimension or depth of the section, and also it varying from this point to this point, it is not constant. If this type of uh, model is used for tensile stress, your bending stress is constant here. Sorry, not bending stress, axial stress is constant. Okay, constant. But if it is used for beam application or bending application, then it is not constant, it is changing from here to here. And you will get the maximum bending stress at the location where your bending moment is maximum. Okay, at location where bending moment is maximum, as well as at highest distance from the neutral axis. Okay, so we need to define the CDEF points. Okay, already I have told you what are the CDEF points. Here we have taken the section, that section is having dimension here. This is your 100, and this one is your 200. Okay, 200. So your C point, what are the coordinates of C point? Can anyone tell what are the coordinates of C point? Kunal Patil, what are the coordinates of C point? If your section is like this, 100 by 200, here it is C point. You have, this is y axis, this one is z axis. You tell me coordinates of C point. Coordinates of C point. Yes.
Sir, I joined now, sir.
Now it is revision of last lecture. Pranjal CLR, can you tell? Here C point is at highest location. Okay. Here you have origin. C point, coordinate of C point is half of this distance. Okay. Here we have 200. So C point is 100, and its Z coordinate is 0. Okay. And I will, here you have D point. This is D point. Okay. It is here in front of Z axis. D point, and its coordinate is, y coordinate is 0 and z coordinate is 50. Y coordinate is 0 and z coordinate is 50. Okay. Now this is your E point, E, and its y coordinate is minus 100, and z coordinate is 0. Okay. And this is your F point, whose y coordinate is 0 and z coordinate is minus 50. Have you got it? Have you got it? This cross section. And here in
Yes, sir.
our, yes, in our problem we have, this is 100, this is 100, and this one is 200. Okay, do you agree with this? Now I will go to the next point. And why we need to define? Because we want to calculate the stress, maximum stress at this location. Okay, your stress is not constant. Okay, now whether this screen is visible, hypermesh.
Visible, sir.
Okay, now we have defined a cross section. This is a rectangular cross section. Okay, now it has dimensions. Already I have shown you. It is 200 and 100. Okay, now here we need to define the CDEF point. Now when we want to define the CDEF point for the beam section, you select this option cont 1. Okay, now here you will get the C1, C2, D1, D2, E1, E2, F1, F2. So here without selection of this CONT1 option, you will not get that points. So you select this cont1. Okay, now C1 is your y coordinate of C, C2 is z coordinate of C, D1 is y coordinate of D, D2 is z coordinate of D, E1 is y coordinate of uh, E, and this is z coordinate of E, this is y coordinate, and this is z coordinate. Now for C1, y coordinate of C is 50, z coordinate is 0. Okay, next for D, y coordinate is 0. For D, z coordinate is, sorry, it is 100, na? 100, sorry, it is. Here it is 100 and here it is 50, because your cross section you can see here, this PPT. Here this is 100 and this is 200. This is C 100, 0, D 0, 50, E minus 100, 0, and this is F 0, 50, minus 50. Okay, now D2 is 50, E is minus 100, and E2, that is z coordinate of E, it is, sorry, E2, it is z coordinate of E, it is 0, F, y coordinate of F is 0, and z coordinate is minus
Minus
50.
50.
Okay, have you got up to here? Okay, now these coordinates we need to define, because your stress across the section is not constant, it is going to vary. Okay, now return from here. Okay, now after that, after defining all the things, return from here. Okay, now now you have to create the component. Okay, now I will create the component. Here bar element property, I am going to give bar properties, and I will keep red color as it is, and say create. Okay, return from here. Next one, see here I will create the two nodes. If you observe, if you take any problem, this is 100 by 100, we have changed it to the 200 by 100. Okay, so I will define the nodes, n nodes. Here first node is at 0, 0, create. Second node is at 500, create. Okay, now one thing I want to tell you here, see here, if you make only one element, लक्षात ठेवा, if you make only one element in case of beam applications or in case of bending applications, then you will get the constant stress from this node to this node. Okay, that means from fix the support to the free end, you will not get variation in the stress. But in case of bending applications, your bending moment is varying from point to point, that means from this point to this point. Okay, do you agree with this? So you need to define the more number of elements. You see here I will show you your bending stress. Is it visible? PPT is visible or not?
Yes,
Present.
sir.
Okay, your stress in this case is not constant from this end to this end. It is changing with bending moment. Are you getting this? Your stress is equation of stress. You see this is varying with m. M means bending moment. So bending moment is varying from point to point. That is, it is not constant. Okay. So your stress is also varying from point to point. If you define only one element, you will get the constant stress. Vary this. So you need to define the more number of elements for beam applications or bar applications. Okay. Now how to do this? I will create the 10 elements for this. I will model this by 10 elements. Now how I can do this? I will show you. See here, for creating the 10 elements, there are different options. You can create the 10 nodes between these two, and you can create the elements passing through these nodes, or you can create the line and you can mesh the line with different elements. Okay. Now first I will create the first I will show you first option by using 10 nodes. Now how to create the 10 nodes? Last time I have shown how to create the one node. Same procedure you have to apply. I want to create the 10 nodes between these two. So you go to the interpolate. Here I want to create 10 nodes between these two. So here you have to put number of nodes between two nodes is 10. Okay, agree with this. Now select the n nodes. See here, bias means you can get a small distance towards this one node, or you can get big distance towards the other node. Okay, that is bias intensity. Bias means if your nodes density of the nodes is required more on this side, then you have to use the positive bias. If you need density of nodes more on this side, you need negative bias. Okay, means number of nodes, distance between the number of nodes. I will show you that. Before that, I will create this linear zero bias. Select this node and this node. Okay, and say create. You see here you got the 10 nodes, or these 10 nodes are at equidistance point. If you want to variable distance, that means if you want small distance towards this node, then you have to give the bias factor. If you want smaller distance towards this, then also you have to give the bias factor. Okay, do you agree with this? You try to do by using different bias factors. You will get idea of it. If you unable to get it, then you can ask me at the time of next practical also. I will show it. Okay, click on create. We have created the nodes, 10 nodes. You can see here. Have you got this procedure? How to create the nodes? Now, after that, you create the bar elements. Now go to the 1D, select the bars. Now you select the properties here. Properties bar, element type C bar, because we have defined bar element. Now this factor orientation is very important. How it is important, I will show you. See here, orientation means it is a orientation of the cross section. Already I have told you orientation of the cross section. Okay, and that orientation should be perpendicular to the length of the beam. Should be perpendicular to the length of the beam. Okay, see here I will show you. If I select the y-axis orientation, then y-axis of the cross section which we have defined, y-axis of the whether PPT is visible, this y-axis will coincide with the y-axis of this one. Okay, if we select the z orientation, then this z will coincide with this z. Sorry, this y. This z will coincide with this y. Means I will show you on hypermesh whether this PPT is visible or not. Yes or no?
Yes, sir.
See here, if I use orientation y, this cross section, y-axis of this cross section will coincide with the cross section of the y-axis of the cross section of the beam. Okay, do you agree with this? म्हणजे हा y आहे तो इथं जाणार आणि इथं y राहणार. Okay, do you agree with this? Now if I take the z orientation, then this cross section here, z axis will coincide with the y axis of the beam. Okay, now I will show you it. You see here, now what I will do, I will create one element by using y orientation. I will select this one. Okay, or again I will do two elements and I will return from here. Now I will check the 3D representation. I will make it in wireframe mode. You can see here. You see here, it is a 200 millimeter and this one is 100 millimeter. Okay, and we have taken y orientation. So y axis of the beam section is coincide with the this y axis. Y axis of the this one, that is y axis of the cross section will coincide with the y axis of the beam. Okay, now you see the z orientation. You can see here. Now I will create two elements by using z orientation. See here, perpendicular to x is y or z, so you can take y or z only. Now I will select z orientation, and if I select this node and this node, you can see here. You see the orientation. Have you got it? Have you got it? Kunal Patil, have you got it? Okay. Now orientation and why it is important, I will tell you. See here, if you take this orientation and if you apply bending load like this, that means in the y direction, then you will get the different stresses. And if we apply the load like this or same load on this orientation, your stresses will be different. Are you getting this? Here you will get the more stresses, here you will get the less stresses, because distance of neutral axis from top and bottom is different. Okay, do you agree with this? That is distance of extreme fiber from the neutral axis. It will be different for this section and for this section. So you will not get the same stresses. Okay, your equation is m by I into y. Y distance is different for this section and this section. So you will not get the same stresses. Have you got it? So orientation is important. If I take x orientation, you can see here. If I select the x orientation and if I draw the beam here, why it is not showing? Okay, it is not correct way. It has shown that, but it should show only line. Okay, I will reject it and I will delete all the elements. See here, that error you will get when we solve the problem. Okay, that x orientation, error of x orientation you will get when we solve the problem. Okay, so orientation should not be perpendicular to the length of the, sorry, it should not be parallel to the x length of the beam. Okay, it should be perpendicular. It may be like this, it may be like this, but it should be perpendicular to the axis. Now I will delete the all elements. Delete. I will show you how to delete. Go to, I will return from here. Go to delete. Select the elements all and say delete. Okay. Now I will create the elements with y orientation. Now I will go to the bars. Here properties, bar property, element type is C bar, and orientation I am going to select as a y. I will go to this one. I will make it in line mode. This one. Okay. Now this we have created all bar elements. Now you can see it is in detailed view. You see these elements in 3D representation. This is element number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 elements we have created because we have taken 10 nodes between these two. Okay, and it is in line mode. Okay, I will keep this in line mode. Have you got this bar element? Now remaining process is same to your rod element. Now next you have to define the load collector. Here I will define SPC, and I will choose this color. Why it is not changing? Okay, say create. After that I will apply the constraint here. All degrees of freedom I will use. See here, if beam, then as 6th degree of freedom is not constant, it will be variable. Okay, that is the rotation about Z is you have to untick. Okay, if it is a simply supported beam. Okay, click on create. Now I will increase the size. Okay, now you can see here 1 2 3 4 5 6. Next I will go to the force. Now I will create here force. Create. Force collector is created. Okay, now I will change the color for force. Okay, now I will go to the force. Now I will select this node. I will apply -1 lakh. It is in y direction and say create. Okay, over. Next one, define the load step. Here I will give the name bar element. Now I will set this SPC and force. It is a linear static and say create. Okay, now I will save it to folder. I will create one more folder, suppose bar folder. Okay, now I will go to the bar analysis. Okay. Save. Now I will go to the OptiStruct. Okay, I will check this export option all, run option analysis, and click on OptiStruct. Over. Now see the results. Now see here this one. Now you will not get a rectangular shape here. Here it is always circular. Okay, visualization bar, for bar I will change to cylinder. Click OK. What happens? Preferences option, visualization bar, I will apply it. Click OK. Okay, we'll check it. Now I will see the displacement. It is a deflection. Click on apply. Now you see here it is a 2.97 into 10 raised to -1. Now why it is not showing cylindrical shape? Sorry, it is bar 3. Here we have to change bar. It is not bar 3. It is just bar. Okay, I will click OK. Now it is, this is the deformation. Okay, now you have you got up to deformation? Pranjal Shelar. Pranjal Shelar.
Yes, sir. Yes, sir. Yes, sir.
Okay. Now I will go to the stress. Now see here in last case, this elemental stresses under this there was axial stress C bar C beam. Now what you have to check, you see here C bar beams long stress SAC. That means it is a stress at point C, which we have defined, stress at point C. Okay, now these options you have not seen in case of rod element. Here these options are for bar and beam element. Okay, these options are not for rod element. Okay, now I will make it simple and say apply. Now you can see here, you see here it is a uniform cross section, area is same, but your stresses are varying. Why it is varying? Because your problem is bending problem. Okay, now you see here it is 7.5 that is 75 Newton per millimeter square into 10 raised to 1, that is 75 Newton per millimeter square. Okay. Now, if we go to the next point, stress at D, and if we apply this stress, that stress will be 0. Okay, because your D point is on neutral axis. Okay. Now next, at E point, you will get the negative stress. You can see here, you will get the negative stress, and it is also 75. Okay, because your cross section is uniform. Okay, distance above the neutral axis and distance below the neutral axis, both distances are same. You will get negative same stress, that is it is minus 75. Okay. Now at F point you will get 0 stress again. Sorry, not F, it is E again. F point, it is 0 stress. Okay, this is the bar element. Have you got it? Yes. Kunal Patil, if you have doubt, you can ask me.
No, sir.
Have you got this?
Yes, sir.
Okay. Now I will go to the next. This we have solved. I have explained the concept of CDEF point. Next, here, how to create the beam elements. Beam element. It is same to the bar element. Beam element, it is same to the bar element. Now I will show you. Just I will go it through it. The steps. Now I will close this. Now same problem I am going to solve by beam elements, not by bar elements. Okay. Now I will go to the new model. Now here also there is problem on beam element. This one, it is same problem we have solved by bar element. Now I will solve it by beam element. Okay. And here I will solve for this orientation. You solve for this orientation. Okay. I will solve for this orientation. 50 and 100. 50 and 100. Okay. Now I will take the Z orientation. Whether this PPT is visible? Yes. Whether it is visible or not? Pranjal Seller?
Yes, sir.
Okay. Now here we are going to solve this problem. Okay. This problem is for Y orientation and this is for Z orientation. Okay. Now what are the CDEF points for this? Here it is C. This is your D. This is your E. This is your sorry, this is this cross section we are going to find. Okay. This point is C. This point is D. This point is E. This point is F. This point is F. Okay. Now coordinates of C point are, Y coordinate is, it is 50, 0. Now for D point, it is 0, 25. 25. Okay. And E, it is minus 50, 0. And C, it is 0, minus 25. Minus 25. Okay. Now I am using this cross section and I am using this problem, that is Z orientation. Orientation I will take Z. Okay. And this problem I am going to solve by beam element. Okay. Z orientation. Now I will go to the hypermesh. Same thing, your material is again steel. Okay. Now I'll go to the material. It is a steel. Okay. Color is this color I am going to use. Type is isotropic. Card image is matte one. Okay. Next, click on create edit. So here this step is compulsory. Create edit. Check E, Poisson's ratio, and density. Okay. Here we have default steel properties that we are using. If you want to change these properties, you can change. Okay. Click on return button. Click on return again. Now next you define the properties. Now you see the properties. Sorry, before that you define the beam section. Okay. Go to 1D, hyperbeam, standard section. Again it is a solid rectangle. Click on create. Now it is, this one is 100, y dimension is 100 and z dimension is 50. It is as per the problem definition. Okay, this is 100, this is 50. Now here it is yz coordinate or yz axis. This z axis, this is y axis. Here you have C point, it is at 50, 0. Here you have D point, it is at 0, 25. At this location you have D point, E point, it is at minus 50, 0. At this point your F point, F is at 0, minus 25. Okay. Now I will close this. I will click on model, view. Okay. Now beam section we have created. Now we are going to use Z orientation. Okay. Before that, we define the properties. Go to properties. Now here it is beam properties. Beam. Now beam element is also 1D element. 1D. Now card image is P beam. Okay. P beam. It is not P bar. Okay. P rod is for rod element. Okay. P bar is for bar element and P beam is for beam element. Now material is steel. Beam section, again it is rectangular section, and click on create edit. Now it is a beam element, so you will get all these properties and some properties we need to define, that is CDEF points. Okay, go to continuation line 2, click here. Okay, and here you have to define C1A. What is the coordinate for C1A? It is y coordinate of C, it is 50. C2A, it is 0. D1A, it is a y coordinate of D, again it is 0. D2A, it is z coordinate of D, it is not minus 25. E1A, it is minus 50. Y coordinate of E, this one is z coordinate of E, E2, or it is z coordinate of E. Okay, F1, it is y coordinate of F0. F2A, it is minus 25. Okay, have you got it? Or any doubt here? If you have doubt, you can ask me. Can I go to next? I am waiting for your response. Preeti Digare, I am waiting for your response. Pranjal Shelar.
Yes, sir.
Okay. Have you got it?
Yes, sir.
Okay. Now I will return from here. Again, I will return from here. Now your beam element is under bars. Again, it is bars. Okay. Before that, you have to create the component. Here I'm going to create the beam component. Okay. Next, I will define the color. Properties are of beam. Say create. Okay. Next, you go to the nodes first. Okay. Go to geometry, nodes. Select this option. First node is at 0. Create. Next, second node is at 500. Say create. Okay. Press a button. Return from here. Okay. Now again I will create the some more nodes. Okay, I will take 10 elements between. I will create the 10 elements. So I need to create the nodes. Okay, in between these two nodes. Go to interpolate nodes. Here I will make it 9 because I want to create the 10 elements. Okay, so select the nodes and say create. Okay, here 9 nodes are created in between these two. Now go to 1D. Again you will get beam elements in bars. Okay, select these bars. Now you change the property beam. Element type is C beam, not C bar. Okay, C beam. Now here orientation, I'm not going to take orientation Y because I want to use this section. Okay, not this section. Do you agree with this? This section I'm going to use. So, but I have created this section in the hyper beam. If I change orientation, I will get this one. Okay. Now I will take orientation Z, or now I will set this as the first node, second node, third node, fourth node, fifth node, sixth node. This. Now you see the orientation by using this 3D detail representation. You can see here this orientation. Okay, have you got it? Now here we have Z orientation. So Y axis of the beam section will become a Z axis of the actual beam. Okay. Now after creating this, I will go back to the main page. Now here I will define the SPC and force collector. Okay, SPC and force collector. Now I will go to the load collector. First I will define SPC. Okay. I will keep this color as it is. I will click on create button. Return from here. Okay. Now I will go to the bars. Sorry, not bars. I will go to the analysis page. Constraint. Okay. I will select this node and I will keep all degrees of freedom constant and say create. Okay. Now after creating this, go to the load collector again, create the force. I will change the color. Okay. Now I will click on create button. Now force collector I have created. You can see here force collector is active. Okay. Now you apply the force on this node. Go to force, and I will set this one node. It is in negative Y direction. Okay, and say create. Okay. Now you can see this one. Force is created. this one. Okay, after that you define the load step, click on this load step. Now it is beam SPC, load is force, and click on create. Okay, now it is same to the bar element. I will save it, save model. Now I will go back and I will create the folder. It is suppose beam. Okay, now I will add the beam, save. Okay, now I will go to the OptiStruct, check the options, export option, run option, and click on OptiStruct. Now it is going to solve. Solution is over. Check the results. Now see the displacement. Apply. Now you can see here it is 1.9. It is same to the last problem because we have solved same problem by beam element. Okay. Now you go to the stress. See here also you will get the CDEF point. Now you get C point. Now this C at C it is 0 because we have used the orientation Z axis. Okay. At D you will get the maximum stress. You can see here, and it is not same to the stress which we have obtained in bar element because in bar we have Y orientation and here we have Z orientation. Okay. Now next stress in A at E, that is again 0. Okay, because your orientation is Z. At F you are this stress. Okay, if you have doubt I will give you 4 minutes, 4-5 minutes. If you have doubt you can ask me, otherwise I will go to the next. We check this. If you have doubt you can ask me. I will not ask one by one. You tell your doubts. Avanti Nalode.
Yes, sir. No doubt.
Have you got everything?
Yes, sir.
If I give the same problems to solve on hypermesh, can you solve it?
Yes, sir. I will try.
No, because you have to submit it for as a submission of experiment.
Yes, sir. I will solve it.
Okay. Next, Indrajit Mohite. Kunal Patil. Yes, can you solve it? Same type of problem, can you solve it? Kunal Patil, I am asking to you. Okay, I think Kunal Patil is not attending the practical. Pranjal Shelar, can you solve it?
Yes, sir.
If this type of problems are asked as a submission of experiments, then can you solve it and upload the solution on Moodle? Pranjal?
Yes, sir.
Okay. Now I will go to the next one. Now you can see the animation of this. I will make it in displacement. You see this one. It is displacement apply. It is 1.919 millimeter is there. It is big displacement. Okay. Now I will close this. Okay. Next one. Now next is this simply supported beam at load at midpoint. How we can apply the load at midpoint, and here I will show you how we can use line mesh option. Line mesh option. Okay. Line mesh option. Now I will go to the new model. Okay. Your problem is, what is problem? Circular rod. Circular rod of 100 millimeter diameter and subjected to 30,000 Newton at center. Okay. I will use simple support for this, not fix the beam, simply supported beam. Okay. Now I will go to the material first. Here I will use steel, color type isotropic, card image matte 1. Okay. Say create, edit. I will use same properties, E, new, row, return from here, return. Next is hyper beam. Go to 1D page, select hyper beam. Now standard section I am going to use circular section. Solid circle, create, and its diameter is 50, so radius is 25. You can check it. Diameter is 100, radius is 50. Okay, 50. Over. Now if it is a circular, not necessary to define the CDEF points. Okay. Or why? Because you will get the same values on both sides. Now I am in hypermesh window. Now I will go to the properties. Here it is beam properties. I will keep as it is known. Okay, I will use circular beam. Type is 1D again. Card image is P beam. Material is steel. Beam section is circular section. Okay, and I will click on directly create, return. Okay, not necessary to change the CDEF points because we have circular section. Next, go to the component. Here I will use circular beam. Okay. Now color I am going to keep as it is. I will keep properties as circular and say create. Okay, return from here. Next, create the nodes. I will create the first nodes. Okay, here by using XY coordinates, end nodes I will create. For creating the line also we need the nodes. Okay, this is your at 500. Okay, create, return. Okay, we have there are nodes are created or not. Okay, we'll check it. It is at 5000. Okay, I will delete the nodes, temporary nodes, clear all. Again I will create nodes, 0, create, where it is. is not created. Zero, 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 say create. Why it is not showing? I will check it. Okay, I have cleared all nodes. I will reopen it. Just wait for a few minutes. Something was happened, I think. So I will do it fast. First, an error message was there. Okay. Material, steel. Next, I will define the color. Type, isotropic, card image, matte 1, and click on create edit. Here I will define the properties, a new row, return from here. I will go to the hyper beam, standard section. It is solid circle, say create, and its radius is 50 millimeter. 50 millimeter. Okay. After that, I will go to the model view, return from here. I will create the properties. It is beam. It is circular beam, we can say. Circular beam. Type 1D, card image, P beam, material, steel, say, and beam section is circular beam. Click on create, return. Next one, after creating the properties, you have to create the component. I will use circular beam. I will define the color, properties of this beam, say create. Now go to the geometry, create the nodes, create. We have created one node. Second node is at 500, create. Okay, these two nodes are created. Now I want to create the line here because I want to use line mesh option. So in 1D, go to bars. Okay, before that I will show you line mesh. Go to line mesh. Okay. Now here select the element type as bar 2 property circular beam. Okay. Now, but here we don't have options to define the orientation. Okay. Now here you define the element size. Okay. Now we have, I will define the element size as a 50. Okay. Now I will set this node. In place of lines, you select the nodes. This node I am going to select this second node. Here with 50 millimeter length, you will get the elements between these two nodes. Okay. Same mesh. You can see here, these are the elements. Okay. You can see in 3D representation. Okay, I will return it. Element density, I will keep it. You can see 3D representation. You see this, these are the elements. Okay. Now after that, after doing this, mesh is over. Now go to the load collector. First is SPC, no card image. Select the color, click on create. Okay. Now go to analysis page, constraints, select this. I'm going to select this and this. I'm going to use simply supported beam with midpoint, load at midpoint. Uncheck this degree of freedom 6 because it is simply supported. Click on create. You can see here you will get the 1 2 3 4 5 6. You will not get. Why? Because this degree of freedom is free. Okay. Return from here. Now go to the force. I will change it to this color. Click on create. Okay. Now for application of the force, you go to here. Okay. Now you see here you have node at this location, node at this location. Okay. Now there is no node at center. Okay. I have to create one node. Okay, I will reject it. Now I will add the node. Okay, I will create the temporary node. I will go to the distance, this node and this node, and I will click on node between. Okay, this is node node at midpoint. Okay, I will reject it. You can get it. Now go to the force. Here, this is a midpoint node, and magnitude I will apply as minus 10,000 in y-axis and say create. It is a force created. Now define the load step. Here, beam. Okay, linear static. SPC is SPC. Load is force. Click on create. Load step is over. Now you save it. Save model. You make one more folder. I will open this folder. I will give the name beam. Save. Run it. You see the results. See the displacement. You can see here. I will change to the visualization bar cylinder. Okay. Now you see here you will get the maximum displacement. You can see the animation. Now displacement is less. Okay. Less. I will increase the scale. You can see this displacement. Okay. Now I will stop this. Again I will check the stresses. element stress at C, apply, it is 0. At D, apply, sorry, it is C beam. Okay, only displacement we got. Okay, now stresses we will check at the time of next practical. Okay, simple, apply. It is not showing the stress. Okay, now here I will stop. Some videos and what we can say, write up for the experiment 1 I have uploaded. You have to do the I will show it. You see here at the end of this slide there is one blank table. You solve all these problems and complete this table. Okay, that is the experiment number 1. Okay, complete this table. This I have shared on Moodle in PDF format. You complete this table and submit it on the link which I have provided. Okay. Any doubt?
Hello, sir.
Yes.
YouTube ला upload करा के lecture, sir.
हो lecture आप करतो. Okay. I will upload it.
Thank you, sir.
Okay, you can leave now.